Our journey into the vast universe of the rare Earth hypothesis and the crucial role of moons and other celestial bodies in planetary habitability unfolds here. This video promises to delve deeply into the intricate gravitational dances and astronomical phenomena that potentially make life possible on distant worlds, all through the lens of the fascinating rare Earth hypothesis. We kick off our exploration by highlighting the uniqueness of Earth. Our blue planet, with its perfectly balanced living conditions, appears to be an oasis of biodiversity in a vast cosmic desert. The rare Earth hypothesis argues that this uniqueness is the result of a complex and highly improbable combination of astronomical and geological factors. It's this rare combination that we're going to explore, especially focusing on the role of moons and other celestial bodies. In this context, moons aren't mere companions to their planets. They can be crucial agents in the creation and maintenance of habitable environments. From stabilizing a planet's axis of rotation to forming tides to directly impacting atmospheric and climatic evolution, moons play a fundamental role that can't be underestimated. But it's not just moons that join in this cosmic dance of habitability. Comets, asteroids, and even the spatial arrangement of planets and moons in a solar system can have profound implications for the possibility of life. Our goal in this video is to unveil these complex and fascinating relationships. We'll investigate how each of these factors not only contributes to the possibility of life, but also what it tells us about the rarity of such conditions throughout the universe. This is an invitation to reflect on our place in the cosmos, a prelude to delving into topics that challenge our understanding of life, the universe, and everything else. Planetary habitability is a concept that goes beyond the mere presence of liquid water, although this is a crucial element. The distance of a planet from its host star determines the amount of solar energy it receives, which is vital for the thermal conditions necessary to maintain water in a liquid state. However, this is just scratching the surface of a sea of complexities. The planet's atmosphere plays a dual role. It must be thick enough to retain heat but not so much as to cause uncontrolled greenhouse effect, as in the case of Venus. Chemical composition is also fundamental, especially the presence of organic molecules and elements like carbon, nitrogen, oxygen, and phosphorus, essential for life as we know it. The rare Earth hypothesis argues that even if a planet is in the habitable zone of its star, the chances of all the necessary conditions for advanced life aligning are extremely low. It puts into perspective not only the importance of a suitable atmosphere and an ideal stellar distance, but also the need for a protective magnetic field that shields the planet against lethal radiation, sustained geological activity that ensures nutrient replenishment and regulation of carbon dioxide, and a stable orbit that prevents extreme climate variations over millennia. Looking at our own cosmic backyard, the solar system, we realize that Earth benefits from a series of fortunate circumstances. Situated perfectly in the habitable zone of the Sun, Earth has a large satellite, the Moon, whose gravitational influence helps stabilize Earth's axis of rotation. This stabilization is crucial for maintaining a relatively constant climate, allowing the evolution of complex ecosystems. Additionally, the unique configuration of the solar system, with massive gas giants like Jupiter, acts as a shield, attracting and deflecting asteroids and comets that could cause mass extinctions on Earth. As we expand our view beyond Earth, we begin to ponder how these principles apply to other worlds. The discovery of exoplanets in the habitable zone of their stars has brought hope but also many questions. How do moons and other celestial bodies influence the habitability of these exoplanets? Are there stellar systems where the configuration of moons and planets offers a protection similar to that of Earth? And more deeply, what are the implications of these discoveries for the rare Earth hypothesis? This enriched context prepares us to explore, with a critical and inquisitive lens, the role that moons, asteroids, comets, and the very configuration of planetary systems play in the creation and maintenance of habitable conditions. We are about to enter a realm where science meets imagination, exploring not only what we know but also what is yet to be discovered. Exploring now the importance of moons in planetary habitability, we dive into a fascinating aspect that often escapes our perception when thinking about life conditions outside of Earth. Moons play a more significant role than simply beautifying our night sky. They can be key to climate stabilization, tide formation, and even protection against radiation on their host planets. The Moon has a stabilizing effect on Earth's axial tilt, which is crucial for maintaining a relatively stable climate over thousands of years. Without the Moon, Earth could experience extreme oscillations in its axis, leading to drastic climate changes and possibly making the environment much more hostile for life. This phenomenon is not unique to Earth. In theory, any planet with a sufficiently large moon could benefit from a similar stabilizing effect, suggesting that the presence of a large moon is a significant factor in assessing the habitability of an exoplanet. Tides, influenced by moons, play a vital role in marine ecosystems and climate regulation. They help mix the oceans, distributing heat and nutrients, and may have been crucial in the origin of life, providing tidal zones that offer a rich environment for the development of complex biology. As we observe other planets, the presence of significant tides could indicate the possibility of similar conditions that favor life. In addition to influencing the habitability of planets, some moons themselves may be candidates for harboring life. Moons of gas giants, such as Europa and Enceladus in our solar system, have underground oceans heated by tidal forces. These environments, protected from the vacuum of space by an icy crust, could be oases of life, challenging our traditional understanding of habitable zones. A moon can offer additional protection against high-energy particles and cosmic radiation. In systems where the moon or moons have their own geological activity, they can contribute to the regeneration of atmospheres or even to the maintenance of magnetic fields that help protect their planets against harmful radiation, an aspect often overlooked when considering habitability. When evaluating the influence of moons on planetary habitability, it becomes clear that their presence and characteristics can be as crucial as those of the planets they orbit. They are not just passive satellites but active agents that can significantly contribute to creating and sustaining conditions favorable to life. Therefore, in the search for habitable worlds beyond our own, science must consider not only the planets themselves but also their celestial companions. Advancing beyond moons, planetary habitability is also profoundly influenced by other celestial bodies, such as asteroids, comets, and even the overall configuration of planets within a solar system. Each of these elements can play a crucial role in creating conditions conducive to life, as well as in protecting habitable planets against potential cosmic threats. Asteroid belts, like the one found between Mars and Jupiter in our solar system, can have a dual role in planetary habitability. On one hand, they serve as a source of organic material and volatiles, essential for the formation of atmospheres and oceans on terrestrial planets. Collisions of asteroids with the early Earth are believed to have been instrumental in delivering water and seeding organic compounds that eventually led to life. On the other hand, asteroid belts can also function as a shield, deflecting or intercepting objects that could collide with habitable planets, offering an extra layer of protection against catastrophic impacts. Comets, wandering through space with their tails of ice and dust, are another potential source of water and organic molecules for young planets. The periodic passages of comets can enrich planetary environments with the essential building blocks of life. Additionally, comet impacts can cause significant changes in planetary atmospheres, some of which may favor the emergence and evolution of life, despite the destructive potential that these events also carry. Dwarf planets and other objects located in the outer reaches of the solar system, such as the Kuiper Belt and the Oort cloud, can influence the dynamics of comets and asteroids, directing them towards the inner solar system or away from habitable planets. These distant bodies, with their long and often eccentric orbits, add a layer of complexity to the architecture of a solar system, potentially affecting the frequency and intensity of bombardment events on planets closer to the Sun. The very configuration of a solar system, including the arrangement of gas giants, terrestrial planets, asteroid belts, and the presence of trans-Neptunian objects, can have a profound impact on the habitability of the planets within it. Systems with gas giants in positions that favor the deflection of potentially dangerous comets and asteroids may protect habitable planets, while an unfavorable arrangement could increase the risk of devastating impacts. In summary, the influence of moons, asteroids, comets, and the overall configuration of the solar system on planetary habitability is a testament to the complexity and interconnectedness of the universe. The search for life beyond Earth, therefore, is not limited to finding planets in the habitable zone of their stars, but also involves understanding the broader dynamics of their stellar systems and the roles that different celestial bodies play in creating and maintaining conditions conducive to life. When we examine the role of moons and other celestial bodies in planetary habitability, our own solar system offers a natural laboratory filled with fascinating examples. These cases not only illustrate the direct influence of these bodies on habitability but also serve as starting points for the search for habitable conditions on exoplanets and their moons in distant galaxies. The relationship between Earth and the Moon is one of the clearest examples of the importance of moons in stabilizing a planet's conditions to support life. The Moon not only helps stabilize Earth's axial tilt but is also crucial for the existence of tides. These, in turn, play a crucial role in the biological processes and nutrient cycles of Earth's oceans. The presence of the Moon has been so vital for the development and maintenance of life on Earth that some scientists argue that without it, complex life may not have evolved. In contrast, Mars and its two small moons, Phobos and Deimos, offer an example of how the absence of a large stabilizing moon can influence habitability. Mars's axial tilt varies significantly over time, leading to extreme climatic variations. This climatic instability has been cited as one of the factors contributing to the inhospitable conditions of the planet today. Looking beyond terrestrial planets, Jupiter's system presents an intriguing case with its moon Europa. Europa is one of the most promising candidates for the search for extraterrestrial life within our solar system, thanks to its subsurface ocean heated by tidal forces. This example highlights not only the possibility of moons being habitable but also the role that forces such as the gravity of a giant planet can play in creating favorable conditions for life on its moons. As detection technology for exoplanets advances, we uncover increasingly complex and diverse systems. Some of these systems contain exoplanets in the habitable zone of their stars, accompanied by moons that could potentially have their own habitable conditions. These discoveries expand our understanding of habitability and suggest that the conditions for life may be more varied than previously imagined. These examples, from the familiar to the distant, underscore the importance of considering a wide range of factors when assessing planetary habitability. The interactions between planets, their moons, and other celestial bodies are critical components of this equation, offering valuable lessons in the search for life beyond Earth. Diving into specific cases can offer valuable insights into how the presence of moons and other celestial bodies impacts the possibility of life. We will examine two bodies within our own solar system that represent the most promising candidates for habitability beyond Earth: Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. Both are oceanic worlds that challenge our traditional understanding of habitable zones. Europa is fascinating for many reasons, but the most intriguing is undoubtedly the vast ocean of liquid water believed to be hidden beneath its icy crust. Tidal heating, caused by Jupiter's strong gravity, keeps this ocean in a liquid state, creating a potentially habitable environment away from direct sunlight. Recent and future space missions aim to drill through Europa's icy surface to explore its underground ocean, hoping to find evidence of life. The existence of a subsurface ocean heated by tidal forces on Europa not only increases the moon's habitability potential, but also expands our definition of habitable zones to include internally heated environments on moons of gas giants. Enceladus, one of Saturn's moons, has surprised scientists with its spectacular geysers, spewing water vapor and organic particles from fissures in its icy surface. These geysers are direct evidence of a subsurface ocean, also heated by tidal forces. The detection of complex organic molecules in the ejecta of these geysers suggests that Enceladus has the basic ingredients for life. Furthermore, the ease of access to samples from this potentially habitable environment through the geysers makes Enceladus an attractive target for future missions in search of extraterrestrial life. The existence of subsurface oceans on Europa and Enceladus has significant implications for the search for life in the universe. These environments offer a new paradigm for habitability, suggesting that life may thrive in places previously considered inhospitable. Furthermore, they demonstrate the importance of moons in maintaining habitable conditions, even in systems where planets are not located within the traditional habitable zones of their stars. The ongoing exploration of these and other oceanic worlds within our solar system could, therefore, reveal not only more about the potential habitability of moons but also about the conditions necessary for the existence of life beyond Earth. The investigation into the influence of moons and other celestial bodies on planetary habitability is not merely an academic quest for knowledge. It has profound implications for our understanding of the universe and our place within it. By broadening our view of which environments can support life, we challenge our previous assumptions and open new avenues for research and exploration. The discovery of subsurface oceans on moons like Europa and Enceladus, coupled with the understanding of the vital role that moons and other celestial bodies play in creating habitable conditions, dramatically expands our notion of habitable zones. This suggests that the search for extraterrestrial life should not be limited to planets orbiting within the traditional, habitable zone of their stars. Internally heated environments or those stabilized by moons in distant planetary systems may equally harbor life. At the same time, this exploration reinforces the understanding of Earth's singularity. Our planet is not only special for its habitable surface conditions but also for its complex astronomical context, including the presence of a stabilizing moon and the protective arrangement of other celestial bodies in the solar system. This reminds us of the fragility of our own environment and the importance of preserving it. The implications of these discoveries for space exploration are vast. They encourage the development of new space missions focused on exploring moons and other celestial bodies, in addition to planets themselves. The understanding gained through these missions may not only answer the age-old question of whether life exists beyond Earth, but also provide insights into the origin of life in the universe. The influence of moons and other celestial bodies on planetary habitability is a reminder that our universe is a place of unimaginable complexity and beauty. The search for life beyond Earth, therefore, is a journey that goes beyond simply locating planets in the habitable zone. It is a quest that challenges our understanding of what is possible in the vast cosmic theater. As we continue this quest, each discovery brings us closer not only to other forms of life, but also to a deeper understanding of our own existence.